So in this video, we'll start looking at a little bit more complicated electron configurations in terms of describing them with term symbols. I keep using that term in terms a lot in this video. So let's say we have a helium atom and we excite one of the electrons up to an excited state. So we have, say, our 1s and 2s orbitals, and we have our electrons like this. Now, I drew it in one particular way, right, where we have one spin up and one spin down, but there are other possibilities as well. So we could also consider a case where we have they're both spin down, or we could also have a case where they're both spin up, or we could have the case where it's spin down in the ground state and spin up in the excited state. Right, so there are four different possibilities here. And these are all valid ways of having one excited s electron in our orbitals here. And so what are the possible quantum numbers associated with this in terms of capital L, capital S, capital J? Well, so the way we'll go at this problem is we'll look at the Z components first. So we'll look at what are the values of capital M sub L and capital M sub S. And that will tell us about what the values of L and S are. And the reason we're approaching it this way is because, as you remember, we're adding vectors, but we don't know all the components, right? We only know the Z component, and we don't know the X and Y components. So we have to kind of glean information from the Z components to figure out what's going on with the overall vectors. Okay, so M sub L is pretty straightforward because these are all S orbitals. L is equal to 0, M sub L is equal to 0, so capital M sub L has to be equal to 0 because when you add up a bunch of zeros, you still get 0. Capital M sub S is a little bit more interesting though. So capital M sub S, let's look at each of our cases that we have here. So we're going to treat all of our spin ups as plus 1/2 for for little m sub s, and spin down is equal to negative 1/2 for little m sub s, right, for each individual electron. Okay, so we have the case, so let's go ahead and just write these values on here. I'll do it in a different color to make it a little bit easier to see. So for our first one here, we have plus 1/2 and minus 1/2. Here we have minus 1/2 and minus 1/2. Here we have plus 1/2 and plus 1/2. And here we have minus 1/2 and plus 1/2. So if we look at the total values as we add these possible values here, so we have a 0 overall here, and these are capital M sub capital S. We have minus 1, we have plus 1, and we have another 0. Okay, so our possible values that we can have for M sub S, M sub L is boring, it's just 0, but here we have three different possible values. We can have negative 1, 0, or positive 1. And we end up with two zeros, two possibilities that have 0, and that is actually relevant. Okay, so we have one set. We have negative 1, 0, and plus 1, and one set where we have just 0 by itself. So that means we have one case here where we have M sub S ranging from negative 1 to positive 1. That means S, capital S, has to be equal to 1. And this extra one here, this is a case where S, capital S, is equal to 0. All right, and so we actually end up with two terms here. Right, our capital L value is the same for both of these terms. All right, so we have capital L equals 0 for both. But then we have one term where capital S equals 0, and one term where capital S equals not 0 or equals 1. Okay, so if we write this and so that means we have one term where capital J is equal to 0, and one term where capital J is equal to 1. So if we write these out, this first one, both of these will be capital S states. And this is confusing because S gets used in multiple places. But our 2S plus 1 that goes as the superscript is going to be 1 for this one where S is equal to 0. All right, so this, let me just make this clear. This top term is for this. This bottom term is for this one. And we have a second one where it's a 3. Right, so 2s plus 1 is 2 times 1 plus 1 is 3. And then our subscript is based on J. So this one's 0 and this one's 1. So we have a singlet S0. Let me spell that right. Singlet S0. And we have a, when we have a 3 here, we call it a triplet S1 term. Okay, and so what's interesting about this is that each of these behaves essentially like its own electronic state. These have different energies associated with them, different selection rules as to which lower energy or higher energy states the electrons can go between. And so it's almost like these behave like their own energy levels. And so we need to understand that these exist, right? That we have these different possibilities that are present.